Good morning, everyone, and welcome. Appreciate you attending today's training. We're going to be covering 9540 UL safety testing. We're going to talk about the test, the certifications. This is a NABCEP certified training. We have NABCEP credits available for this talk. So if you're here for those NABCEP credits, please stay through the end. I will check the registry, the attendance logs, and issue your credits. So if you're here for those NABCEP credits, please do stay through the end. I'll put up my email address at the end. So I'm going to point out a couple of things as we get started here. First, if you have questions, please do feel free to use the Q&A feature. Ask those questions. I will try to get answers back to those questions in real time. And if there's some questions that I don't get to as I'm making this presentation, I will jump to those questions at the very end. We'll cover them, and we'll hopefully have some time for a back and forth with Q&A. I do want to point out as we get started with this presentation on the 9540 testing that the battery market is growing. Currently, only about 15% of solar owners have battery storage, and about 61% want battery storage. Another statistic, similar statistic, says only 11% of solar owners have battery storage, and 33% are expected to have battery storage by 2027. So slightly different numbers there, but these show you the rise in the growth of battery storage. And important to that is the consideration of safety, the type of battery you use, the safety of the battery system that you install. So again, my name is Nathan. I'm an energy trainer here at Briggs & Stratton Energy Solutions. And I want to point out that Briggs & Stratton is committed to battery safety. Understanding battery fires, understanding battery safety, understanding battery backup and installations in homes and businesses is very important. So one of the things that Briggs & Stratton does is participates in the National Fire Protection Association conferences to help educate and create safe industry standards. We understand the importance as this field emerges of everybody learning together. And we appreciate that you are learning with us today. So the 9540, UL 9540 test, why does it matter? Well, it introduces a standard for safety. It introduces certifications so that inspectors that might not have the time to learn everything about different battery technologies, right, can rely on those standards when they're doing their inspections and when permits are being issued. Energy storage systems contain both electrical and fire hazards, right? So you have large amounts of currents that'll pass through these battery backup systems. And there's a lot of energy packed into these small battery modules. Additionally, there are fire risks associated with these modules, and we're going to get into them today. So as technology becomes more common, stakeholders need to consider and evaluate the likelihood of a thermal runaway. And it does happen. Large fires can happen with batteries. And this is why, right, we need to pay attention to safety. The market is evolving, and there's a lot of new technology being introduced. It's impossible to stay on top of everything. And this is why there's this need for standards, which is what the underwriter laboratories do in creating these battery safety tests and safety standards. So we're going to talk about what the 9540A test is today. It's a test, not a certification. It's a battery safety test. And we'll get into that test, and I'll show you what the test looks like on some of our batteries. And of course, firefighters are concerned about the very high heat release rates of batteries. You have lots of energy packed inside these batteries, and it's quite possible, because you have flammable materials in lithium-ion batteries, to have a fire that is difficult to put out. It's hard to get to these fires as well, because if the cells inside battery cabinets are burning, There's no easy method of getting that suppression material, the water, into those modules, the things that are actually burning. And cells to cells can cause fire just by conduction of heat, right? There does not necessarily need to be a flame in order to get these cells to off gas, and I'll explain why that's the case. What's inside a battery module? Let's start off with the basics here. There are a lot of different types of lithium-ion batteries, right? And these are not always identified when people are selling batteries. Oftentimes you just hear, well, it's a lithium-ion. There was a lithium-ion battery fire, right? Well, there are a lot of different types of lithium-ion chemistries. Typically, these are based on the cathode material, the different metal oxide that's used to absorb the lithium as the battery discharges. Cobalt-based chemistries, there's a number of different types: NMC, LCO, lithium magnesium oxide, LMO, NCA. NMC is probably the most common lithium battery that's out there. And one of the reasons that these cobalt-based batteries get used is there's a very high energy density and they're lighter weight than LFP batteries. However, energy density and weight are not particularly huge factors when deciding what kind of batteries to use for building and home battery backup. And in that situation, I feel that the only safe battery to be using is lithium iron phosphate-based batteries. Lithium iron phosphate batteries has a number of advantages. One, these types of batteries, they have a slightly lower voltage, slightly lower energy density. However, they get a lot more cycles. You can get almost twice the number of cycles with lithium iron phosphate batteries, and there's a greatly reduced fire hazard with LFP battery chemistry. And for this reason, most companies that are in the industry are moving towards LFP batteries. Additionally, even companies like Tesla, I'm forgetting some of the other major car brands, but even car manufacturers are switching to LFP. 2022 was the first year that more than half of Tesla's cars produced were using LFP battery technology. Longer living battery, much safer. But additionally to the chemistry that used, there's also how the battery is built. There are different types of batteries: cylindrical cells, pouch cells, prismatic cells. Pouch cells are probably the most dangerous of these cells because they're very easily punctured. Cylindrical and prismatic cells are more rigid and a little bit more protected. We only use cylindrical cells. These are premium cells in our batteries. They have a closed steel casing. All of these batteries have to be combined, whether it's pouch cells, prismatic cells, or cylindrical cells, to produce larger battery modules. So cylindrical cells, like I said, are the cells that we use in our batteries. I'll show you in a second what can catch fire with these cells. They are steel cased, they're hermetically sealed, but that seal can be broken if a great enough temperature is reached. Prismatic cells are essentially these foil wrapped packs of basically a sandwich material that we call a jelly roll, where you have a metal oxide, you have an organic electrolyte between that metal oxide, and then you have a graphite layer on the other side. And so what can burn with these battery cells is that organic salt solution, that organic electrolyte. All of these cells have them, all lithium-ion batteries. We're hopefully moving towards solid-state batteries in the future, but for right now, all of the batteries that are on the market for home battery backup have this organic electrolyte inside them. It doesn't matter the chemistry, they all have that electrolyte, and that's what allows the lithium to move from the positive to the negative side. So what if you took a cylindrical cell and you unwrapped it? It would look something like this, where you have an aluminum foil that's coated with that metal oxide. In our case, it's a lithium iron phosphate layer. And then you have this organic electrolyte in between. It's throughout that roll, and then it's on the other side, it has a copper foil. And this is all rolled up around a steel core, which is what makes up an individual battery cell. In the event of extreme heat, what can happen is this electrolyte that's inside the jelly roll can get hot enough that it turns into a gas. It can go from a liquid into a gas. And if you get too much pressure inside one of these cells, and it can actually burst a vent on the top that's designed to prevent explosions and do what we call off gas. That gas can burn, as I mentioned. Now, in the case of pouch cells, you might have seen a pouch cell that looks like this before. That's actually my hand holding an old iPhone battery that I'd taken out. It had burst, and it had burst to the point where it was bulged out, but it did not actually catch fire. But what can happen with these batteries is that they can off gas. And like I said, pouch cells are the most dangerous because they're the most easily punctured. So to create a full battery module, a full what we call battery, right? The module is composed of many, many cells that are in stacks. And these cells have to be arranged in series to create higher voltages. A nominal voltage of a LFP cell is only around 3.2 volts. So to create a 48-volt battery, we actually use stacks of 16 of these and get voltages slightly above 48 volts for a charged battery, and that voltage varies. But basically, all of these batteries have cells arranged in series, and there is a risk of something called thermal runaway. And that's what we're going to be talking about today, the UL standards for safety and testing. But in the event of a thermal runaway, what can happen is that that gas, that organic electrolyte, right, can catch fire. And you might have heard about the Samsung Galaxy Note 7. Now, this is probably 5 or 6 years ago, but this phone was banned on flights because of an internal short circuit failure, which would cause this battery to actually catch fire. If you imagine a single, so what is thermal runaway? If you imagine a single cell catching fire, that cell is going to release a lot of heat. So for whatever reason, if there's a maybe car accident, or if there's a car runs into a garage battery, you can have an event in which one of the cells can be damaged. That cell, if short-circuited inside, can release its electrical energy in the form of heat and can off-gas. If that individual cell off-gases and catches fire, it can get hot enough to warm the cells around it. And so basically, you can end up with what we call thermal runaway, which is this chain reaction in which multiple cells start catching fire and they catch the ones next to them fire. Spoiler alert, our battery cells are fairly safe. And in fact, with LFP batteries, you very rarely are going to run into events where you have thermal runaway. And in fact, we don't have events with unmitigated thermal runaway. By contrast, I'm showing two pouch cells here. This is a YouTube channel that I watch fairly often. This is Will Prowse, and he's showing the puncture. He punctured two different battery cells, an NMC battery cell and an LFP battery cell. And you can see the drastic difference. The rate at which the heat is released with an NMC cell, this is a cobalt-based chemistry, is very high. And in fact, after drilling a single hole in this cell, it rapidly started off-gassing. And shortly after that, the heat ignited that off-gas into flames. And this burst into flames in a matter of seconds. With an LFP cell, he did puncture an LFP cell, and he had to puncture it multiple times in order to even get it to go into an off-gassing event. And when it did off-gas, so you can see he's drilled almost 10 holes into this cell. When it did off-gas, it releases that heat much more slowly, and it never actually caught on fire. So it's just some independent confirmation of what I'm saying. We only use LFP. Now, here's some industry issues associated with battery fires. I'm showing a nail penetration test, the top left there. This is an LFP penetration test on the left side, and then a penetration test with an NCA battery, nickel, cobalt, aluminum oxide battery. And you can see that NCA battery going into a battery cell going into a rapid off-gassing event with flames. So very rapid release of heat with these cobalt-based batteries, which is why we, Simplify Power got started about 13 years ago now. That's why from the very beginning, Simplify Power which focused on safety, has only used LFP battery technology. And it seems like the industry is catching up and catching on. Much of the industry is now also, for home battery backup, going towards LFP. There are some other cases of fires. These are 2019 fires. I'm showing LG Chem, and I know that LG Chem has switched to a different technology now, but they had to do recalls because of safety reasons. So it is important that as we present battery options to customers, that they are aware that fires can happen. Now, these are large-scale industrial type fires. Even Tesla, this is a fire from 2021 in about 2 years ago. In Australia, and now this was a cooling system that was required for their NMC battery cells that apparently failed here. But it does highlight the fact that NMC cells need cooling systems in order to stay safe. With LFP, that is not the case. So the topic today is to get into UL 9540 test method, 9540A test method, and the 9540 standard. And I'll explain what those mean. Essentially, this was developed in 2017, and this test is here to inform about the safety of battery cells, modules, and units, right? So an individual cell, depending on its manufacturer, its type of design, its chemistry used, can have varying levels of safety. Modules are what we would typically refer to as a battery. That's a complete battery operating at a voltage with typically a BMS unit in it. And then a unit would be a complete set of batteries to make up a backup system. The test evaluates thermal runaway, the risk of unmitigated propagation and fire, and the deflagration risk, so explosion risk, in energy storage systems. And the data is used primarily to determine the relative safety of batteries, to set some industry standards, and to inform for permitting reasons about sizing, etc. So I'm going to take a second to check the Q&A. And yes, Sean mentions that I did not include LTO on that slide. I'm not sure why I dropped that off, but lithium titanate I have mentioned before actually involves a different anode instead of a different cathode, and I guess that's why I decided not to include it. I have included it previously. Thank you, Sean, for mentioning that. One of the things that's very nice about lithium titanate is you can have very rapid C rates without producing all that heat. So thank you, Sean. Eric says 9540A test results are available for the Simplify Amplify batteries. Are 9540A test results available for the 4.9 battery yet? Are the 9540A test results available for the high voltage modules? Great questions, Eric. And yes, we've made some rapid production advances here. We have a 9540 test wall set up at our test facility, and we have UL inspectors coming to run tests at our safety and testing facility in Oxnard, California. And I can say that the 9540 high voltage test model has completed the 9440 up to the unit level. The 95 on the 4.9, the 9540A, it's not available on our website yet, but it's also been completed up to the unit level. And then the 9540, which is the certification. So the tests have been completed. The 9540 on the 4.9 battery within a couple of weeks should be certified as a standalone ESS. And so we are kind of in the process. We have a test wall up there now testing multiple different configurations. And one of the things that we can do, since safety factors are built into the advanced battery management system of these communicating batteries, is actually certify these as a DC ESS, which would allow the 4.9 and the Amplify batteries to be used with any inverter that's got the 1741. So yes, those test results should be available very quickly, very soon, within the next couple of weeks, and they have completed the 9540A tests. So thank you. That's a great question, Eric. So let's get into the 9540A test. Let's explain. I'm not going to go through. There's a lot of text here on the screen. I'm not going to go through everything in detail, but I'm going to point out that the test starts at a cell level test. So if you are working with cells that are so safe that you do not need to worry about fire at all. Then you would not need to go through a module level test. However, with all lithium-ion technology, the cells are not, safe enough to say that they could never go through a fire, and they all have to essentially progress from a certified UL cell up to a module level test. And that module level test will allow you to test the battery safety in general. So testing the complete battery, and I'm going to show you our test results for 9540A on our modules. And then from that, we could go up to a unit level test where you can combine many different battery modules. And for us, our battery modules are safe, and we did a unit level test, and we've passed this test with flying colors, I would say, and we do not have to do installation level tests. So if you had a battery that had questionable safety, you might actually have to do an installation level based test with UL, which can create a lot more complexity for getting your permits. So essentially the test starts with a series of progressively larger tests involving forced thermal runaway. What that means is that they basically take the battery cells, heat them up so much that these battery cells off gas, and start down the path of a thermal runaway. Now, this is artificially forced to create a condition in which the cells will go into a thermal runaway. This is a test. It's a testing standard which informs the manufacturer as well as UL about the safety conditions that should be put into place for approved designs, and I'll show you that later. It also helps us. It helps manufacturers and system integrators meet the IFC, the ICC, and the National Fire Protection Association 855 by evaluating the safety, basically the effects of the safety in terms of thermal runaway, fire protection, and explosion. If you had a battery that was prone to explosion, you would probably have to put that inside some type of deflagration cabinet to prevent issues like that. Also evaluates and determines inherent safety of the battery chemistry, form factor, manufacturing design, the safety features that we build into our batteries, and it helps to determine spatial requirements, such as how closely the batteries can be placed together for an installation. The 9540A, the primary concerns of fire codes like NFP 855, which addresses how installations in homes and businesses can occur, is to address fire potential and explosion potential, right, associated with battery systems. To control hazards, codes specify limits for energy capacity. So based on the results of these tests, you might have limited size banks that you can put together. Our batteries are quite safe, and so we don't have limits on many of our batteries. And of course, our battery cabinets have limited sizing. The latest IFC and NFPA 855 editions allowed code authority to approve larger individual ESS units. And so there is some level of decision-making that does go to individual AHJs, for instance. The UL 9540A does provide data that you need to design risk management or risk mitigation and allowance to exceed installation and or distances. It's also a joint US and Canada safety standard. And so this is both in place in the US and Canada, particularly in California, New York, and Florida at the moment. These are the states that are paying the most attention to UL 9540 and those that are often asking for UL 9540 test reports when issuing permits, etc. UL 9540 is a set of standards an energy storage system must perform to. UL 9540A is a method of evaluating thermal runaway propagation in an ESS. The 9540A is the test. The 9540 is the certification. This test result, as I mentioned, is now, it started in around 2017. It's now in its 5th edition as of a year ago. fire, thermal, and explosion hazard, deflagration radius. Some batteries have venting requirements for off-gassing. In fact, New York City requires off-gassing monitoring system, and we're one of 3 manufacturers that's approved by the Fire Department of New York to install our units in New York City in high-rise buildings. NMC chemistries have seen higher instances of thermal runaway, fire propagation, and explosion recall. So I just want to point that out there, that the chemistry really matters. And NMC, both in testing results as well as in situ, in the environment, right? NMC has a poorer history with safety. LFP chemistries have proven far safer both in the field and by tests. Other states are adopting results based on this 9540. The 9540 test results basically are used in combination with a 9540 report. Separate versions for residential and commercial, so that we have different different testing standards based on the destination and the type of battery. I've got another question from Eric. He says, UL 9540 evaluation provides measurements of off-gassing, outgassing, volume and flammability of each component gas, and fire propagation cell module unit. How do you propose containment of outgas components to minimize the possibility of ignition? And does the BOSS cabinet and/or cabinets for high voltage systems provide outgas containment and ignition minimization? Do the cabinet systems require ventilation to open air for this mitigation? The cabinets are vented to open air. The cabinets do offer a deflagration barrier. Of course, these are built very heavy steel, and the cabinets offer deflagration protection, but there is no containment of outgas components. None of the batteries that I'm aware of have the ability to contain off-gassing. There are certain batteries, especially those batteries more prone to fire and off-gassing, that have to have special gas monitoring and outgas components to minimize. But with LFP batteries, they do not. So let's move along. The UL 9540A test method is used also for insurance and fire mitigation professionals. And insurance companies are paying more and more attention to the safety, especially as a flood of new batteries coming from new companies is hitting the market in the US with this rapid growth of battery storage systems, both in the form of cars, but also in the homes and RVs, etc. Insurance are paying attention, and they need to be able to understand what the test results and what the test method provides, and be able to assess the risk associated with having those batteries installed. So let's go through the UL certifications for batteries. They start off at a cell level, which is the UL 1642. So this is a cell level cell level safety test or certification. And basically what happens with this is that you take battery cells of different chemistries, different constructions, and you subject them to the kind of abuses they might see in the field. Shock, the battery gets dropped. Vibration, the battery is being transported in a vehicle. Drop testing, heating, battery is sitting in a car that's overheating, or potentially there's a fire in a building next to a battery. Temperature cycling, as a battery heats up and cools down, heats up and cools down as it charges and discharges. Low pressure, what would happen if this battery cell is in a low pressure environment like the cargo hold of an airplane? Short circuit condition, the battery is accidentally short circuited, or even damaged to the point where a short circuit occurs. Again, heating, abnormal charging, so the charging control mechanism breaks down. You force a discharge on the battery at high rates, well above the rated discharge ability of the battery. You crush the cell. impact the cell, humidity tests, etc. If the cell survives these abuses and is able to pass minimum standards, it meets the UL 1642 cell safety testing. And from that, you would be able to use that cell to assemble larger battery cabinets or larger battery modules. So batteries based on many cells. And so this would be a module level safety test as the UL 1973. So this tests the battery itself. And this would include the BMS safety features that we have there, such as overcurrent protection or temperature shutoffs, etc. So that's the UL 1973 safety standard. And then the UL 9540A is, as I mentioned before, a test protocol. And we take all of our batteries through this. It's successfully completed for the 5 3.8, the amplified batteries. All of our batteries based on LFP battery cells have gone through UL 9540A. As I mentioned, just very recently, we've put our high voltage 3.8 batteries as well as the 4.9 battery through UL 9540A testing. Test results concluded that the cells and battery modules do not produce fire or cause fire propagation. Even when forced into thermal runaway, these thermal runaways self-extinguish. We also have UN 38.3. It's not on here, but this is for transportation of our batteries. You have to have this in order to be able to ship your batteries. And we have this on some of our batteries are approved for shipment on airplanes as well, but they have to be under a certain weight limit, which I believe is 86 pounds. Then UL 9540 is a safety standard. Once a system has gone through safety testing and has met the standards of UL 9540, you will gain UL 9540 status. And that's with after having completed a successful UL 9540A test. There are codes associated with batteries and installations. So codes associated with the installation include the NEC, of course, the National Electric Code, but also the NFPA 855. And you can read about standards, for instance, where batteries can be installed. They cannot be installed in a living room, for instance, or bedrooms. They have to be installed in non-living space locations. So you can have battery-based rooms in a house, but they do have to have a certain thickness. I believe it's a 5/8 inch drywall, et cetera. And there are minimum distances that are laid out in the 855. The ICC is the International Fire Code and International Residential Code, and these codes set standards for installations of battery systems. Additionally, there's battery safety certification. There's the UL 1642, the UL 1973, and the UL 9540, and these are the ones I just highlighted. And of course, there's the UL 9540A testing method, which we are going through. So just to point out that we have these BOSS cabinets and access cabinets, which actually include an inverter in them. These are certified to UL 9540, and they've gone through the UL 9540A safety testing. And of course, each of the batteries has the UL 1973. These are meet the battery energy storage system installation instruction, or we have to follow the installation instructions to maintain this UL 9540 rating. Basically, the 9540A test proves the effectiveness of the safety systems that we've built in. Let's get into it. What does a 9540A module level test look like? Well, essentially what we do on a module, what we mean here is a battery module composed of many cells. We take 7 of the cells within this module and heat them with thermal wraps. So we're taking these cells at the very top. We're having many thermocouples in this unit to monitor the temperature. And so some of these wires that you see here are wires to heat battery cells, and then wires for thermocouples to monitor the temperature of those battery cells. The battery cell labeled M that is here is going to be monitored, and it's an initiating cell, meaning we are going to heat this cell. We are very carefully monitoring many locations. UL is carefully monitoring many locations to find the heat at different locations here. So what we look at here, so we put these wraps on these cells, we heat these cells. These cells are heated to the point where they actually go through an off gas, and they're continued to be heated until that off gassing results in the cells around that those initiating cells to also off gas. So this is basically a forced fire. And here are some of the results. So what you can see here as we heat the battery cells more and more and more, remember cell number M, that initiating cell on the top center there, you can see its temperature rising here. You can see the cells around it have their temperature rising. And we get to the point of venting. So venting is when the pressure inside the cell from the electrolyte turning into a gas gets high enough that it bursts the safety vent at the top of the cell. This is where off-gassing starts. Thermal runaway, we actually see occurring, and remember, we're forcing it into thermal runaway at around 35 minutes in. So after about 35 minutes of heating, we get thermal runaway, and then we see this temperature rising, and rising. And this is with what we call propagation. So propagation is the cells around that cell also starting to catch fire and off gas as well. But what you see with this test result is that these cells actually end up self-extinguishing, and that temperature starts to come back down. And so within an hour, we're back under 100 degrees Celsius, and within 200 degrees Celsius, and a couple hours, we're back down to lower temperatures. So this forced thermal runaway does result, of course, in off-gassing. And you can see that here, that we're looking at the volumetric flow rate here, liters per minute. What we're doing is we're monitoring the gas coming off these battery cells. And so you can see that initial off-gassing, of course, that occurred on the left graph around 24 minutes, shows a spike in gas occurring here. And then another one is indicated. These are just markers indicating those times. But what you can see is a fairly low, steady level that's below 10 liters per minute, more like around 1 liter per minute. And then we're also looking at smoke release, and the smoke release rates here are very low because they're monitoring, assuming that many cells would be going into thermal runaway. And in fact, we have just a few of the cells that actually go into thermal runaway. So these are the smoke and the off-gassing monitoring system. So we're looking at gas coming off the batteries and smoke. Here's an example. So we're showing you this battery. So we were able to successfully pass the module level test, and we're going to do a system level test, a unit level test now, where we take a battery module and we put that battery module into a whole system of many batteries. I believe we did 36 of our 3.8 batteries. We have 93 thermocouples for this UL test placed inside this battery cabinet. And then UL conducts these safety tests. And so we also monitor external temperatures, internal temperatures, etc. We're doing this for a 137 kilowatt hour system. So this is 3 of our battery cabinets. It's an equivalent to the size of about 10 power walls, for instance, a very large system. And then we do this, we're looking here at the safety spacing between these cells, and we also specified that this should be done in an 8-foot tall room, so an 8-foot tall ceiling. And this is to replicate conditions that we would expect in, for instance, a garage install. So in this particular picture, you can also see that there's a bag over top of this module in the back left corner. This is the module this is the unit that is being heated. And so the bag is there to capture gas that's escaping. Additionally, like I said, we're monitoring temperature here. What we're going to do is notice battery module 8 is going to be the one that's going to be forced into fire. And this is pretty much the worst battery you could think of to catch on fire. It's low in the cabinet. It's sandwiched by 2 other batteries. So if it does have heat, it's harder for it to get rid of that heat. It's going to be most likely to cause batteries around it to get hot. And so we've chosen this one because it's kind of worst case scenario. If we chose the bottom one, number 11, then it would be able to cool a little bit faster because it's at the very bottom of the cabinet and it doesn't have kind of thermal mass below it to keep that heat in. And so basically we're going to catch battery module 8 on fire intentionally. We're going to force it into fire, and we're going to measure all these red dots on these batteries show places that we are going to have thermocouples attached to be able to monitor the temperature in different locations. We also have those on surfaces as well, but this is what it looks like. We have these battery put back together with the forced ignition wires and all the thermocouples coming out. On the right side here, you're looking at a list of all the thermocouples that were there for this module. This is the result of that test, essentially. The results for the subject battery were identical to the module level test. So when we forced it into a thermal runaway, we got limited propagation. We were only able to propagate to a few cells, only 2 cells directly adjacent to the 7 cells that were intentionally heated, actually went into a thermal runaway. So we have very minimal propagation there. We didn't even get many of the other batteries many of the other cells in the battery to catch fire. So no module to module propagation. In fact, the temperature of the unit only went up to 55 degrees despite this forced fire that occurred inside the unit. No fire or explosion risk. There was no explosion from our batteries. So, this is a fairly unremarkable test, a fairly boring test, I guess, if you were looking for fire, but good safety results for us. So the highest temperature recorded at all was 60 degrees Celsius at the adjacent batteries. So these are the ones right next to the battery that was caught on fire. And the temperature dropped rapidly after the test was over. Temperature rise in adjacent batteries was very unremarkable here. So what we are looking at is the results of all these thermocouples on this module. And we're looking at the unit temperatures here, and you can see that venting does occur, thermal runaway does occur. Of course, we forced it, we wanted it to occur. And then that venting results in the release of some gases. Associated with this is smoke release. And so the markers here are showing you when venting occurred, when thermal runaway occurred, and you do not see large rises in smoke as the result of this because essentially it was self-extinguishing. You can see the temperature rise occurring. So as the battery is forced into thermal runaway, we are monitoring the temperature on the rear wall, the side wall, and the soffit temperatures of these battery cabinets. And you can see a slight rise, but overall the temperature of the battery cabinet stayed about room temperature. So even though we're forcing a fire inside one of the batteries inside our battery cabinet, overall the test was unable to create very high temperatures or even warm temperatures outside the battery module that was forced into fire. Ceiling height, again, we had this reduced to 8 feet to show more constrained space. 0 hydrocarbon gas released and no flames observed. This is observables during the test. So essentially, these are the results of our report, and you can gain access to this report by going to the website. I'm going to pause for just a second and look for questions. One question comes in. It seems to me that the battery management systems with integral measurement of module and submodule temperature could provide an excellent early warning of potential thermal runaway. This could allow predictive and preemptive, instead of reactionary, mitigation of potential battery fires. Is communications between fire monitoring systems and battery energy or battery management systems being considered? Well, in fact, Eric, our batteries are battery management systems actually do have protection built into them. And that's one of the reasons that we believe our batteries are going to be able to pass 9540 as standalone batteries that can be used with any system. When high temperatures are released, there's an internal contactor that the battery management system, the BMS computer inside the battery, has control over, and it can actually open circuit. It can do this in cold environments as well for safety of the battery, the safety of the integrity of the battery. So, but in terms of external communication, our battery management systems do communicate with external equipment through CAN bus, but I'm not aware of, we don't, at least at this time, have communication with fire monitoring systems. I do know that in New York City, we do have a solution that involves I think it's lithium-ion tamer, I think is what it's called. And it's a management system that is designed to work integrated specifically with our batteries. But to my knowledge, the BMS right now does not communicate with external systems. And in fact, our batteries have such a high safety standard that they've built that there's not a great need for that with our LFP batteries. It is potential that other NMC type batteries will have more advanced monitoring and even cooling systems, right? And so that's one of the points of using LFP is it's safer and you don't need those systems, which allows modules to be produced safely without spending large amounts on cooling and safety equipment. Rich Moore asks, how many documented thermal events or fires have occurred in a residential installation in the past 5 years? Is this a regular event for residential installations? That's a great question, Rich. And unfortunately, I really don't have any information about how many fires have occurred as a result of batteries. Fires occur for many reasons, right? In fact, there was a car fire recently on the highway near me that closed down lanes. This was a gas-powered car, not an electric car. But I don't have information about this. I do not think it's a extremely common event, but it has to be considered, and they do happen. Yes, they do happen. And if you're using less safe batteries, either due to the type of construction, undersizing of wires, ineffective battery management systems, etc., it's probably more likely. There's also the possibility that other equipment can fail. There's an example of equipment, I'm not going to name names here for companies, but there's a failure for a company in which high voltage can be passed through a charge controller directly into batteries. And that can cause damage to the batteries and potentially fire. So I don't know, Rich. I will try to get that information because that's something that I probably should include in this presentation, the frequency of documented thermal events for residential installations. So great question. Eric asked, could you address the battery structure that appears to contain thermal runaway to the immediately adjacent cells in a module? Let me go back. So battery structure that appears to contain thermal runaway in immediately adjacent cells. Yes. So I think what you're referring to is the fact that I mentioned that we had 2 cells that resulted after we forced the 7 cells, we had 2 cells inside this battery module that did also result in off-gassing events. What appears to contain the thermal runaway is, I think the fact that the cells themselves are steel cased, and the heat transfer rate between cells is low enough to not be able to get additional cells to catch fire after the heaters were turned off. So essentially, we had turned on heaters around 7 of the battery cells. That resulted in those 7 battery cells off-gassing and resulted in 2 cells around them also resulting in off-gassing. And then when those heaters were turned off, the off-gassing stopped propagating heat and no more cells. And to give you an idea, there are several hundred cells in each battery. And so it's a very small number. I'm not sure I answered your question though, so feel free to clear it up or ask additional questions or even email me if I can do better. So again, the results of our test, this is with a 3.8 kilowatt, and this is a cabinet basically which we're not getting flames, we're not getting a lot of carbon dioxide and carbon monoxide produced because we essentially, the test was ineffective at producing a large scale battery fire. peak chemical heat rates, like I said, the smoke and heat rate was very low because we were not able to generate, or UL was not able to generate large-scale fires with our batteries. Here's some pictures from the actual test, and spoiler alert, they're not very interesting. In fact, it looks almost like the same picture, but if you notice the timestamp on UL's videos there, it's showing the battery cabinet before and after the test. This large set of wires that you see here is a bundle with all of those thermocouples and testing wires. Again, they're monitoring temperature in almost 100 locations, monitoring off-gassing, etc. So the end of the test looks essentially like the beginning of the test. We do, of course, have one battery module that is damaged. So one battery was damaged, the one that was forced into fire, into thermal runaway. Here's an example of a cobalt-based competitor test. Yes, I guess the idea here is to be shocking, but this is an example of what a test can look like with an unsafe system, right? And this battery module would, I would imagine, fail the 9540A, 9540 certification, certainly, and the 9540A test result would likely require, if this battery is going to be used, some very extreme safety conditions under which it can be used. Again, one more time, ours, essentially, you can't even see the damage, even though we tried to force a battery into a fire condition. So thinking about what the inspectors are doing, you know, they're going from building to building, looking at many different systems. So the value of 9540 is to accelerate the permitting process, make it easier for inspectors to know what's safe and what isn't safe. And what you're seeing here are letters to our company certifying that we've passed the 9540. We've essentially showing the safety, and then a letter from the Fire Department of New York to one of our employees giving the certificate of approval. Like I said, we're one of 3 companies that has it. And so we have that approval to install in New York City and even in Skyscraper. One of the things that would be nice to see, and since our company focuses so heavily on safety, we'd like to see other companies actually releasing their test reports. So we released our test reports and our results, and I'll point out on the website where you can get information and get access to those. It'd be great to see other companies doing that, releasing their reports. Differences between residential systems, EV and smaller devices. It would be great if we could clarify types of battery chemistries and the differences between different things, such as, I mean, we've got cars coming on here that will be parked in garages, similar to ESS systems that are going to mount in garages. It's important to note the type of chemistry, not just calling everything a lithium battery. It'd also be great to create risk profiles based on test reports and evaluations that industries can use when they're designing large-scale systems. And with new technology, loss of historical data is not readily available. Test reports can create guidance in terms of engagement with companies like fire companies that are trying to create protocols and standards for dealing with events. So again, we have a list of our certifications and test reports. You can find more on product documentation. This is a quote from Ken Boyce. He says, UL 9540 has requirements for what we want to see going on inside the energy storage system. This is UL's Senior Director of Principal Engineering and Industrial. We look at making sure the cells are appropriately proven for safety and that they're being integrated into the system the right way and have the right software and hardware controls to govern the functional safety of the unit. Again, the whole point of this is to guarantee safety for the installers and their customers, the end users that are going to have this in their home. And that's the whole point of this test. I know it can be challenging to get all the information. Mr. Abina says, can the LFP battery's energy density be improved? Well, essentially, LFP battery energy density, it's the amount of energy the battery can hold per kilogram. Yes, you can increase energy density by making layers thinner, etc. And doing so, however, can shorten lifetimes. So cells are often designed for different specific purposes. So for instance, C rates, how quickly you can discharge a cell or a battery. And if you want to discharge it really very quickly, you will design it in a way that has shorter pathways for heat to get out, etc. But if you want it to last longer, right, there are ups and downs to changing the design in different ways. So yes, energy densities can vary even for LFP batteries. It's unlikely that the energy density of an LFP battery would ever match that of a NMC battery, which is about 20% more. And this is why I expect there's going to continue to be a use for batteries like NMC batteries in devices where weight really matters, right? You don't want your laptop computer to weigh, 20 pounds. You want it to weigh 12. You don't, well, maybe even less than that. You don't want a drone to weigh 10 kilograms. You want it to weigh 4, right? So again, it's not a major consideration for home battery storage because typically these are not mobile solutions. These are just batteries sitting in cabinets. Maybe it's 20% harder to lift in, but I don't think it's a major challenge. So it's a good question, but I think it's not a major consideration for us. In fact, we're much more concerned with safety. We would rather have our batteries built in heavy metal cases to keep them safe than to reduce weight, because most of our customers are not asking for a lighter home battery. They're asking for a longer lasting, safer home battery. Will this training session be put on your YouTube channel? Absolutely. So we'll be putting a recording of this, and I will be sharing all the slides with you. There were many slides where just had too much text and it took, would have taken too long to go through in detail, but I want you to have a copy of the slides, so I'll be sending these out. Obana says, how can I know a typical BMS has thermal runaway protection? It's a good question. I think you have to ask those questions when you're purchasing that BMS, right? Whether or not it has, safety built into it. Does it have a breaker built in? And does it have temperature protection? And often this is advertised by the companies that are selling it. Of course, our batteries, our BMS in the Amplify, the Simplify 4.9, newer batteries all have these things built in. UL 9540 certified and test cabinets. We offer these, of course, to the public, and we even have on the right side, that's actually an access cabinet with a Solarc unit inside. And we've gone through the 9540 testing with our high voltage batteries as well. We have a whole high voltage commercial and industrial division. So if you're not aware of that and you're interested, please reach out to me, training@simplifypower.com. And I will connect you with those engineers that can help you design a commercial and industrial project if you have one. So again, we offer these solutions. I do want to point out on our website, so if you go to simplifypower.com and look at the very top, you'll see a section that says UL 9540 there. Please take a look at that if you're interested in learning more, obtaining our test reports, etc. You can get access to all of this. We publish this. We wish our competitors would do the same. So please feel free to look at UL's testing of our batteries and get those results there on the website. One more thing I want to point out is that we have, if you are an installer, we do have a program for elite installers, and there's a bonus structure that we pay out to installers that install our batteries. Again, if you're here for NABCEP, this wasn't a NABCEP approved training. You can get 1 hour of NABCEP continuing education credit by sending an email to me, training@simplifypower.com. Let me know how your name should appear on your certificate, and I will get those issued. Typically, it takes me about 24 hours to get responses to all of you. You'll be getting a copy of these slides, and I imagine tomorrow sometime, if you've registered for this training, you'll get a copy of this video. So thank you again. I appreciate it. I'll check one more time for any questions. Jack Hughes mentions that I should invite you to contribute training ideas as well. And I do want you to take the opportunity to suggest training ideas. You can send an email to training@simplifiedpower.com. I think we'll also try to create a form for you to respond to. So we appreciate your attendance. Thanks, everyone.